So plants drink in CO2 from the atmosphere, from the air, and water from their roots. And with solar power, they turn it into life. And where's the carbon in the picture?
Everywhere.
Everywhere. It's in the air, it's in the cow, it's in the plants, it's in the soil, it's in the fungal organisms and the other microbial organisms in the soil. And then life takes all of that matter that the plants have turned into themselves and other things and organizes it in ways that affect the flows of water. And this is my river, the Umpampanoosuc River, the watershed that I live in Vermont. And we play there and swim there and hang out there in winter and summer and spring and fall. But one year, things got a little bit wild, and that was 2011 with Hurricane Irene. And the river jumped out of its usual course, and we lost 500 miles of roads and 300 bridges in one day. And at that point, I was working in holistic healthcare, and I was writing about resilience and sustainability and public health. And I suddenly got very interested in water, soil, and climate and how they were interconnected. I decided to shift my career from being a holistic healthcare provider to writing things for people to help people learn about these systems, and I put it together into a workbook called Understanding Soil Health and Watershed Function, which has now been downloaded for use. It's a free resource by 40 countries and 29 different states in the US. And while I was working on the last chapter of that, called A Walk in the Rain, which was about going out and walking through landscapes, these are still Irene here, to look for how does rain interact with the soil surface? How does rain interact in your landscape? And I was imagining people walking around and doing, little videos of little puddles at the corner of parking lots. This is the road that we walk on every day behind our house, and this was July 1st, long after Irene, just this last July 1st. This is what it looks like now. So it's not just one storm that we have to recover from that we haven't paid for yet. It's recurrent storms. And it's not just storms, it's also that our soils aren't acting as a filter anymore. So we have things like this, algae blooms in Lake Champlain and many, many, many lakes around the country and many, 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 parts of the ocean where we have toxins that create public health problems, both for people and for the rest of the environment. So one of the exercises that I developed in this curriculum is the flour and bread exercise. And I'll take a plate of flour, and we're going to pretend that those flour particles are the sand, silt, and clay broken down rock particles that make up the substrate of soil. It's just the mineral substrate of soil. And when they don't have any biology in them, they have no relationship to each other in terms of how they fit together. They're just a pile of loose material. And if you poke a hole in a paper cup and try raining on that kind of soil, which is what soil reverts back to when it's degraded by poor management decisions, then what happens there? And some of you have seen this exercise before. But what's happening around the edge of the plate is a flood. What's happening in the center is that the soil is running off. Anyone who's made bread knows what that's like when you pour the water on the flour. So you have a drought and flooding in the same landscape. You put that out into the sun in Africa, and you've got a baked-on surface that rain can't infiltrate into, and then you have even more drought and flooding because the water, instead of moving down, is moving sideways. If you have chemicals in the landscape, they're ending up in the waterways, and the aquifers aren't refilling. So what do we need to add to flour to turn it into a sponge, into bread? Biology, thank you, microorganisms. So same is true for soils, and those microorganisms take those individual particles and knit them together into a very porous, absorbent matrix, and it's a living matrix. This is the work of living organisms that creates a living tissue that has a respiratory system and a digestive system and a reproductive system. And as my friend John Norman says, soil is living tissue. We need to think about it that way. You wouldn't just take a shovel and stick it into your dog, right? So when we dig in soil, we are cutting into living tissue. So let's look at what this looks like in an actual landscape. And this is something called a rainfall simulator that the Natural Resources Conservation Service, their soil health team, has been going around, particularly in the Midwest, doing these demonstrations for farmers. And on the far right is the soil that's like the flower. It's degraded soil. It's just mineral particles. It has a little biology left, but not enough to create that living structure. And that living structure has also been basically been put into a blender with the tillage, the cultivation, right? So it's been all chopped up. And if you imagine putting that bread into a blender, would it still be absorbent? No. So underneath, these are like big cookie cutters that have been cut out sections of soil, and underneath they're empty, open. So you'll see there are jars in the back, and on the far right, the jar in the back is empty. So they've put 4 inches of rain, like with a big shower head, over these trays, and on 3 inches of soil, nothing has gone through. And if you flip that pan over, a big cloud of dust comes up, which is what the people who run these shows call the oh shit moment, because all of the farmers standing around who've been taught that when rain is coming you need to till and open up the soil realize that they've been taught wrong, that it's not true that tilling the soil will make it more absorbent. And in the front you have the runoff, catching the runoff, because the pans are at a little slope. So you can see how much soil material has run off, and like I said, that's also carrying any chemicals that are used on the land into the waterways. Now on the far left, you have soil that's been managed according to soil health principles, which are based on the same principles that any healthy landscape works with to build that sponge. That's what nature does on land, is it builds a sponge. You can leave it alone and it will do it as long as it hasn't been so degraded that it doesn't need a little extra help. So this is on the far left, you have a no-till managed grazing system. So you have animals, you have worms, you have microbes underground, you have plants feeding those underground organisms, all working to create a sponge. And what happens with the water? It's all infiltrating, it's all going down, it's getting clear and filtered by the physical filter of the sponge and the biological processes that will break down anything that's not supposed to be there, put it back to its original parts, like just carbon and nitrogen, etc. And nothing's running off. So empty jar in the front, full clean jar underneath. And it's a progression there from the far right to the left of soils that are under different types of management, moving from extreme kind of industrial farming to the most thoughtful, natural, regenerative farming. So, so where does Walter come into this? Well, I met Walter at our conference of Biodiversity for a Livable Climate conference at Tufts in 2015, when 2 of my students, were doing this exercise. And he was talking about the soil sponge. We didn't have that language of calling it a sponge, but we were showing that. And he said, hey, you're showing exactly what I'm talking about. So we got talking afterwards. And I got a chance to host Walter and his friend Tom up in Vermont for a few days and realized, hey, this is an opportunity to share this further. So last year invited him back for a 3-day conference in Vermont. And at that conference, we hatched out this idea that we don't need to start more nonprofits or do a film or do this or do that. Walter said we need to organize our activities around an audacious goal. And the audacious goal, the audacious goal that Walter proposed, even though we were on the East Coast, was can we rehydrate California? So California had been in a 5 or 6 year drought, and when it did rain, there were mudslides, all kinds of things. There were wildfires. The Central Valley, where 40% of the food in our country is produced, is turning into a desert. The rainfall has dropped. There aren't even as much, there's much less fog rolling into San Francisco. And we know how living systems create rainfall, create the sponge, create everything we need to know to keep a system going. And I think people in California know a lot of the pieces, but they don't have a way to put it together into a narrative. So this year, Walter and his friend Cindy in Australia and I worked together for the past year to put together a tour of North America, starting in California under the heading, Can We Rehydrate California? And we had 7 events in which people got very excited to hear these systems thinking about land function and how they might apply it to that landscape. Then we went to Kansas and did the same thing there. And now we're here, and then he's going up to Ontario and Ohio, and the movement is building. And we're hoping that Massachusetts faces many of these same issues. You know, we think, oh, well, New England is fine, but what do we have? We have flooding down at the waterfront. We still have a lot of issues with water quality. We have a lot of impermeable surfaces. We have food that has lost its nutrition, which this is an issue of, and we have this warming that's happening that Walter will address.
And we had a drought for 2 years.
And you had a drought for 2 years. So this is part of this Soil Carbon Sponge 2018 tour, and we're really happy to have you part of it, because what we want is to keep turning it over and say, here are some principles, here are some ideas, what do you want to do with this? So without any further ado, I'll turn that over.
Okay.
Didi,
Okay.
you want to press the up button for the screen?
Yes, and I'm going to leave you with one more question here, which is, so this is the infrastructure and which Walter will talk about, of the soil carbon sponge. Which do we want to spend our money on? Repairing this infrastructure or this infrastructure? Which is a more permanent solution? This one or this one? Okay.
Okay.
What did you want me to do? Push
The
that?
up screen.
Press the screen up button.
Over here? Okay. Screen up. Well, we can save the world, but can we press the screen up? Okay, I'm seeing program volume, projector, laptop.
It's context sensitive, so if you're
Context.
not,
Oh.
that's right. So
Oh.
if you're not part of the
Depends on
context,
who's
Yeah. It's got to be in the know, right?
Maybe we need to do this screen.
who knows? Here we go.
Okay.
Yes. Hey. Yay.
Okay, we can do anything.
Adam. Hey, no wonder he's called Adam, isn't it?
I was the first troublemaker, but not the last.
Oops. Right. Hang on, Adam. Halfway up. You've got to hold the button there, you see? Yeah. All that forbidden fruit, you know?
I'm going to get my water. Can't live without water, not even for a few minutes.
Right. Well, look, thank you very much for coming, and a very, very great pleasure to be back here. I'm a bit overdressed, but they sort of said, should I put a tie on? And I said, I've got a maroon one. And hey, that's Harvard's colour, so, you know, you might as well put it on. But even if I'm overdressed, no, we're pretty down-to-earth people. I'm really a soil microbiologist from down under. Most of my time I spend just quietly underground, you know, just doing work there. But no, very interesting things. I'm working with a little group called Healthy Soils Australia in Australia. They're groups of farmers, very, very innovative farmers, all different industries, all different regions. We've got about 1,000 farmers involved in this in Australia, but they're really leading some very, very clever solutions, both regenerating the land, but then coming into rehydrating arid landscapes, and of course, naturally, safely cooling those regions and the planet. So I wanted to sort of share all that experience, but also what's happening globally at a bigger level with you, and really come to the topic of today, you know, new climate solutions. a bit of a pun on solutions, because we're going to be talking about hydrology and basically how 95% of the heat dynamics of the blue planet is governed, in a sense, by water. And in a sense, it's a process and a whole influence that we've, in a sense, ignored in the last 60 years with this climate debate, because we were so focused on the CO2 rise and the symptoms of that, and of course, what do we do to address the CO2? And in a sense, water is just the key process that naturally drives the hydrology, drives the heat dynamics of this planet. And really the question is, can we actually look at those processes and see if they are part of the solution? But, okay, no, please come around. No, no, okay, because no problems, interruption. And it all comes back to the thing that Didi sort of talked about, because at the end of the day, it's where do we humans have agency? What is it we can do? Because where are the practical points of influence? And of course, that is that simple word that she said, the sponge. How do we regenerate the Earth's soil carbon sponge? So in terms of take-home messages, it is that sponge, it is a regeneration of the sponge, which is our key tool, our key point of agency, but also it enables a whole regeneration of biosystems, gives us the water, the food, the biosystems, the social stability we're going to fundamentally depend on in the next 10 years and beyond, but also allows us to naturally and safely cool regions in this planet. And so in essence, that's the new climate solutions we want to talk about. But let's get into some of the details of that. Basically, we've all known for the last 60 years, and we've all seen, actually I'll do in the middle here, we've all seen the curve that Charles Keeling sort of set up in 1958, or from 1958. Okay, that's CO2. This is time. And basically CO2 goes up. It's 406 parts per million. It started at 280. Okay, and what Charles Keeling showed wasn't just that CO2 was going up, but that it was going up in a quite clear pattern where every winter we were emitting carbon, and every summer, spring, of course, we were drawing down carbon from the air back into biosystems. And so we had this constant springtime, summertime drawdown, and then winter emission. And the point was that we had a deficit of some 10 billion tons of carbon per annum every year. And basically, it's that deficit, that accumulated deficit, that was causing the CO2 rise. And of course, for the last 60 years, that's been our whole focus in our climate, global warming discussion. Clearly, we have CO2 rising. No question whatsoever, CO2 is a greenhouse gas. We know it does about 4% of the heat dynamics of this blue planet. It's a major or partial contributor to the natural greenhouse effect, and certainly by increasing it, we are accelerating that greenhouse effect. We know that effect is serious because if we draw the Earth, we know that we have incident solar radiation, that's sunlight coming into the Earth all the time, and on average at the top of the troposphere, 240 watts per square metre. The constant heat energy coming into the top of the troposphere. 342 watts per square metre. And basically, to keep a stable climate, it's just simple physics and simple climatology that we need 342 watts going back out. Obviously, otherwise the climate heats. But it's not, because now, because we've increased the greenhouse effect, the retention of heat by this planet, we only have 339 watts per square metre going out. So there's about 3 watts per square metre which is being retained by the Earth because of this enhanced abnormal Greenhouse Effect.
What's the time factor in that?
This is a constant, this is a continual heating. It obviously varies enormously, latitude, seasons, etc., okay? But this is a constant energy in, energy out balance, and trying to keep it very simple, right? So it's a 3 watts per square meter warming, which is really what the global warming is about. And it's significant because obviously it's changing the climate, but we can see that is less than 1% of this incident solar radiation. And it's important to understand that context because, hey, 1%, we may be able to do something about it. But of course, here we're talking about heat dynamics, but we've got to now translate, hang on, here's the CO2 increase and how do they relate and what other factors may be involved. And of course, we're raising that proposition. The water, what role does water play in this? But we'll come to that as we go through in a bit more detail. Look at this, we've got a monster duster.
You want us to wait for questions till the end? Or?
No, look, because we've got 2 hours, I'm happy to sort of, like explain things and go as we go along. And so please don't feel shy. You sort of come and ask questions. But the bigger discussions of where we're going and stuff, we'll integrate a lot at the end, and Didi was going to lead us through that. But please.
Yeah, I'd suggest if it's something that you didn't understand, just a factual question
Yeah.
that you need in order to build your understanding, go ahead and ask it. But if it's something that's more of a discussion, we'll be doing that at the
Yeah.
end.
Okay, well, this is a factual question.
Good.
On the Keeling curve, we have a northern and southern hemisphere
Yes.
that are offsetting each
Yes,
other.
yes.
Is the reason for this that there's more land surface on the
Yep.
north of the equator, or is it that they don't mix?
Okay, no, well, look, very good point. Well, obviously seasons differ, right? So summer and winter are different, so that all obviously offsets each other. And you're absolutely right. The southern hemisphere is dominated by oceans, whereas the northern hemisphere has got much, much more land mass. So this is much more pronounced in the northern hemisphere. But overall, again, we're taking a global, average measure. But certainly, yeah, this is more pronounced up north. And also it's more pronounced, obviously, where you've got deciduous forests and what have you, than tropical forests, because they, in a sense, growing more evenly. You still have the same curve, but not with the same pronounced thing. Okay, no problems. So we've already set the scene, you see, because we've sort of said we've got 10 billion tons of carbon every year that's adding to the atmosphere. And so in 1978, your president, Jimmy Carter, basically sort of said, look, I'm getting this warning from scientists legitimately. And basically he issued a reference to the Scripps Oceanographic Institute in San Diego and Los Alamos to say, look, do the analysis and tell me what is the consequence of this greenhouse warming, what are the risks to America, what are the impacts to America and globally, and really give me a reference, give me the grounding, where do we have to be and what do we have to do. So that was Jimmy Carter in 1978, right? 40 years ago. And of course these institutes, they diligently did that work, but they defined the thing very much on the basis of this CO2 effect. They sort of said, okay, we've got this symptom, we've got this CO2 increase. Obviously it's abnormal. And so how do we look at the greenhouse effect of that CO2 rise? They were well aware, and climatology 101 right from the 40s, 50s, was fairly cognizant, 95% of the heat dynamics of the blue planet is driven by water. But they basically excluded water from their analysis for 2 reasons. The first thing is because water is so dominant, they assumed that, look, we humans could not possibly have influenced that aspect of the world's heat dynamics to have had this effect. And secondly, because water, again, is so extremely variable in time and space, location and seasons, it's impossible to model mathematically in the reference that the president had given them. Can you mathematically model and define scenarios and consequences, what will happen? The point is that they basically focused on that CO2 component of the greenhouse effect, assuming that that was the key problem, and that's what we were having to address.
Well, there's something else involved. The amount that CO2 stays in the atmosphere for thousands of years, whereas water goes in and out of the atmosphere
Totally.
very rapidly.
Totally.
And the real problem is cloud formation.
Totally, we'll come to that, absolutely. And I mean, that was the point. As I said, it's so variable in time and space. It goes in diurnally, every square meter, every forest or grassland or concrete urban area. It is just so variable, dynamic, it's almost impossible to model, right? And clouds, we'll come to clouds because they're part of the solution we'll be talking about. Okay, but I'm just setting the scene because the reference, the context in which the analysis being built from 40 years ago was looking at the CO2 greenhouse effect. And the point I'm trying to make is that we're just really looking at a small part of the global heat dynamics, and the elephants that we haven't looked at aren't in the room. They're far too big to be in the room. They're still outside. Okay? These 95% of the global heat dynamics driven by hydrological processes have never been seriously considered. They basically then came, Manabe, Weatherald in the 70s, basically took the reference and yeah, they came up with a curve. Basically, yes, we increase the CO2, yes, we can get an increase in temperature. But just like Cervantes Arrhenius in 1896, when he'd done those calculations initially, the CO2 rise was relatively modest, about 0.2 of a degree centigrade from doubling CO2. So they integrated a water vapor feedback effect as part of their modeling process. Okay, well, very simply what it happens is as you increase the temperature, the amount of water vapor in the atmosphere increases. And of course, air at higher temperature can hold more water. And basically they said, okay, if we assume that the temperature is increasing because of the CO2 effect, it will hold some more water, and therefore we can include that water vapor effect as part of the CO2 as a secondary feedback. It's getting a bit technical, but basically, so they included some of that, but they've never looked at water as an independent factor, which is in a sense what we're going to be focusing on. Because of this analysis though, really for the last 40 years, the world has been really focused in that linear concept of the CO2 greenhouse effect and what's its consequences in global warming. Shortly after, in 1988, the UNFCCC, the United Nations Framework Convention on Climate Change, basically was formed and took on a global reference to say, look, we must prevent dangerous climate change happening. And all nations, in words, committed themselves to it. And out of that, they formed the IPCC, the Intergovernmental Panel on Climate Change. And for the last 40 years, those scientists working in the IPCC have been basically, again, doing this sort of analysis, looking what are the consequences, the impacts, the scenarios from this rising CO2 increase. But very much focused on the CO2, leaving aside a lot of the hydrological and other factors. Again, too complex and too difficult to model. Okay, so we, for the last 40 years, have looked at this problem from very much that CO2 angle. And so when we're talking about new solutions in climate, we're really sort of saying, okay, can we step outside with the elephants and start asking questions from the other perspective? Because 10 years ago, or actually no, 2005, so that's now 13 years ago, Joachim Schellenhuber and a whole group meeting at the Hadley Centre sort of really did a new analysis and said, look, it's not just the CO2 rise that's the problem, it's actually the dangerous extremes in climate that are already accelerating and happening well in advance of the 2,100 scenarios that this IPCC analysis had sort of given warnings about. And these extremes, were actually already impacting seriously on populations, food productions. And they're quite severe. I mean, and we've talked about them, the hurricanes, the increased storms, whether it's Irene, Sandy, what have you, the flooding and the damage, as Didi has sort of shown all over the world from that, but also the droughts that are as a consequence of that, the aridification, the systemic aridifications of large regions, the increased wildfires, and of course things like sea level rise. And the point about all of those factors, all of those impacts, they are all hydrological. They're all driven by actually water, either the excess or the absence of it, triggering things like fires, droughts. And so the analysis was very clear. These extremes, these positive feedback, dangerous feedback loops were already accelerating. And particularly in countries like Australia, and in fact all Mediterraneans like California, the Middle East, the Mediterranean, South Africa, we've had a process. If we think again, there's the Earth, there's the equator, you've got the heating, and we've got these Hadley cells, which causes air to rise from the tropical heating zones. And of course, it rises up and descends as dry, hot air. And because of the heating of the planet, this has expanded both northward and southward by some 300 kilometers. Okay, so the intensifying heating from this whole greenhouse effect, from this 3 waters already causing that. And of course, this extra heating has forced the cool, moist feral cells, it has forced these cool, moist feral cells, which really drove the rainfall in Mediterranean climates, the winter, the reliable winter rainfall, has forced that further towards the poles in both cases. And as a consequence, from 1975 already, the southwest of Western Australia was already aridifying, and a 20% decrease in rainfall, a 30 to 40% decrease in stream flow, soil recharge. Because again, it was rainfall, but also evaporation factors. So we were aridifying, and the same thing applied here in California. I don't win a prize for drawing the country, but basically the whole southwest of the US, again, under that aridification. Same thing is the Middle East. Okay, Spain, right across to Syria, basically has been aridifying. And of course, we're already seeing the consequences of it. For the last 15 years, we've had farmers who've been farming the Fertile Crescent in Syria, for example, for the last 10,000 years, abandoning their farms, moving into Damascus, Aleppo, because their soils, hydrology, everything has collapsed, can't grow food anymore, moving into these urban concentrations, and of course, we know as a consequence we end up with social collapse, social crisis. So this systemic aridification, just one of those fundamental consequences of these climate changes that are already occurring. So the whole point, that was 2005, dangerous climate change. Okay, dangerous climate, actually not just change, basically extremes, right? And it's these extremes that become then the really dangerous consequences. And in a sense, that's the world we're now facing, intensifying dangerous climate extremes, and the issue, what can we do about it? Now finally in 2015, after lots of political work and false starts with Kyoto and what have you, the IPCC, Christina Figueres in Paris, was able to pull down a general agreement to say, look, let us all agree to try to achieve zero net carbon emissions. Zero net carbon emissions. So in the Keeling curve, they're saying, okay, can we actually try to get back to neutrality where our emissions and our drawdown of carbon, in a sense, offset each other, and we end up with a near zero net. And that's very laudable, and of course, to do that, there's been a big agreement, a move. How do we increase the drawdown of carbon back into the by the biosystem, back into soils, and carbon sinks? And of course, yes, we have to do that. Of course, we have to continue to try to reduce, I'm drawing the arrows the other way, we're trying to reduce the amount of emissions, and definitely that has to continue. Nobody is for a minute suggesting we don't have to reduce our emissions. But the power is, can we actually accelerate that drawdown of carbon back into the biosystems? Every year, some 120 billion tons of carbon is drawn down by green plants back into the biosystem. But it's not good enough, because every year 130 billion tons of carbon is actually emitted, which is where we get this 10 billion tons of carbon deficit. But we can increase this, because at the moment the residual biosystem that we have, the land surface still covered by green photosynthetic vegetation, is perhaps half of what it was 8,000, 10,000 years ago. Okay, again, there's all the data, the numbers, we can go through them, but basically UNEP very clearly defined, yes, we have done so much degradation of forest, of grasslands, we've created 5 billion hectares of man-made desert and wasteland over that 8,000 years. And the issue is, can we increase the drawdown of carbon by regenerating that biosystem? And so a lot what we're talking about is, yes, how do we do that? How do we enhance that? There's a bigger problem, however, because while this might be able to sort of slow down the emissions of CO2 and flatline them, well, we're up here now, of course, it won't bring that CO2 down. To bring the CO2 back down, we not just have to do 10 billion tons to offset our current net emissions, we might have to do another 10 billion tons per annum to actually draw back heritage legacy emissions that we've basically emitted previously. So the target might even be bigger. It might be 20 billion tons of carbon per annum. And the good news is, yes, we can do that. We can do that through land regeneration by extending the area, the productivity, but particularly the longevity of green growth. Okay? But none of this is possible, and this is a key point, none of this is possible unless these biosystems have water. Okay? Because for these biosystems to fix carbon, to draw down carbon, they need water. And that water can only come from the soils. So the whole take-home message from can we draw down, can we try to balance this, is we must regenerate the Earth's soil carbon sponge, because only that water can enable this drawdown to operate. Okay, so that's really important. That sponge is fundamental to that whole photosynthetic potential being realized.
So I lived in California, and the major problem was the Colorado River that was drying up.
Yep.
And the fight between all
All the users, yep.
So the question is, I agree that you have to bring water to the soil.
Yep.
But where's the source of the water coming from?
Good, we'll come into that. We'll address that.
Just one quick comment to that, because I hear this a lot, that it's not that we have to bring water into the sponge, it's that we have to build the sponge so that when it rains, the water comes down and stays and doesn't evaporate again.
Spot on. See, so the point is, exactly the point. We'll talk about both fronts. We'll talk about where's our rain, you can sing the song, what have they done to my rain and how do we get some more? But then also Didi's point, it's not how many raindrops we get that really matters, or does matter, but just as important, what happens to every raindrop? Do we let it run off, basically erode, fill dams and overflow to the sea? Or do we keep it in that sponge to keep on feeding resilient longevity of green growth? But we'll come into this because you're getting right to the guts of what we're about, right?
We like beavers.
Well, we're better than beavers. We've got to be better. But beavers are good. Yeah, beavers are good, but yeah, we can do better. We lift this up way past that. But we have another problem, okay? This is another problem, because even if we are able to draw down 20 billion tons of carbon, and we can, innovative land regeneration can do that. We're going to Sweden to a conference, negative net emissions, and yep, here's the evidence, 20 billion tons. Jim was talking about that as well. Yes, we've tested it from all angles. Yes, we can do that. But even that's not good enough. Because even if we draw down 20 billion tonnes, even we draw down 50 billion tonnes, the oceans contain 30,000 billion tonnes of carbon. And as we draw down more carbon from the air, the oceans say, thank you, can I re-equilibrate some of the carbon that we've been absorbing from all your emissions over the last 8,000 years back into the air, because it's a buffered equilibrium system. And so it may take 100 years, 1,000 years for drawing down carbon before the CO2 content gets anywhere back to pre-industrial human intervention. And the point, 30,000 billion tons of carbon dissolved, as CO2 dissolved in the Earth's oceans. That's not counting the limestone and the chalk and the corals. This is just CO2 dissolved in the ocean's water. That's why they're going acid. But the point is, as we draw down carbon from the air, this is a buffered system, and it will re-equilibrate. So we're going to have to do much more than just linear processing. This is a major task. Effectively, because Schellenhuber has told us dangerous climate extremes are already happening, we're already seeing those, flooding, droughts, aridification. California is on the cusp of collapse. That's why we went there. No more snowpack. No more groundwater. No more coastal ranges rehydrating landscapes through fog and mist. Wildfires in winter. The Napa Valley burnt in winter. Winter was when these Mediterranean areas should be getting their moist, cool air. Fires were unheard of in Mediterranean areas in winter. Okay, the Napa Valley burnt last winter. So the point is, we're getting these climate extremes, and we haven't got 100 years, we haven't got 1,000 years, we've got perhaps 10 years unless we balance the system. So this comes to the second key point we want to talk about. It's not just regenerating the Earth's soil carbon sponge, but how do we naturally, safely cool regions and the planet? And again, very audacious. Nobody's actually talked about it. Well, some people have, clouds and what have you. But the point is, how do we bring that back into the debate, not just as a debate, but as a practical grassroots reality? How do we practically cool, safely cool regions and the planet? So that's exactly the challenge we've given ourselves. Okay, so this has really been to set the context of what we're about. How do we actually regenerate the Earth's soil carbon sponge? And of course, how do we naturally cool the planet? We've always said why we have to do it. And I suppose the next question is, well, if this is why we have to do it, let's get busy and ask what is it we have to do? And how do we do it? Logical, right? So what is it that we have to do? And of course, the easiest place and the only place we can go to say, well, look, what did nature do? How did nature create this biosystem? How did nature create the Earth's hydrology? How did nature create the Earth's natural cooling? Okay, because it was 342 watts in, 342 watts out, stable, right? Stable for hundreds of millions of years. Hey, how did she do it? Okay, and to do that, we just go back into nature and look at all the evidence, very clear. And we go back to 420 million years ago when I was a bit younger. I'm getting old. And basically 420 million years ago, we had oceans, we had rock. Dry, arid, hard rock. No life on land. There was complex multicellular life in the ocean after the Cambrian explosion, but that life depended on nutrients leaching from the rock into the oceans. That was a limiting factor on ocean life. And life's pretty competitive and pretty aggressive, and so straight away life sort of said, hey, if I can get onto that rock to solubilize nutrients, I've got a competitive advantage. And it did just that. And so it grew tubes of cytoplasm basically onto the rock with enzymes to solubilize essential nutrients. And of course, these are our fungi. So fungi grew from the estuarine edges onto the rock to solubilize nutrients to drive life processes further. But fungi are just like us. They're heterotrophs, actually biochemical. There's nothing closer to us as animals as these fungi. Okay, and they're just like us. They can't fix their own sugars. They can't make their own energy. Only plants and algae can do that, and some bacteria. But basically, they needed to form a relationship, a symbiosis, with something that could give them sugars. And of course, in the ocean, there were plenty of blue-green algae. So these fungi and these algae got together, made a deal, and basically said, look, let's form a lichen. And we see those lichens all over this planet still, dissolving rocks, dissolving our buildings, our concrete, our wood, our cars, you name it. Lichens are eating it up, biodegrading it, having lunch. Okay, and those lichens, in growing and moving on, leave behind organic detritus, the cell walls of those fungal, algal, lichen cells, organic detritus. And that organic detritus can hold water. It creates sort of a mixture of mineral particles, organic material, can hold extra water. And that enabled very rapidly, plant life to evolve from lichens to mosses to ferns to cycads to gymnosperms to angiosperms, and about 50 million years ago, grasses. Parallel with that plant evolution, of course, we had the herbivores, the insects, and everything that was feeding on those biosystems. Very rapidly, that process of pedogenesis, of soil formation, because soil is simply a mixture of mineral particles and organic detritus, enabled life to extend right across the 13 billion hectares of ice-free land on this planet. Okay, so within 100 million years, we had a planet which was the Carboniferous Permian, just lush, deep forests, deep organic soils, teeming with life. In fact, so teeming with life that the drawdown of carbon got down to carbon levels in the atmosphere of 100 parts per million. When life had started on land, it had been 7,000, 8,000 parts per million, and had drawn all that carbon into those forests. And of course, that's where we get all our coal, fossil fuels from that Permian Carboniferous fixation of carbon through these plant materials.
Well, the other thing is that in forming soils, you form clays. And the question is, are lichens good clay formation?
Yes, lichens form good clays because by breaking down the mineral substance, exactly, you get clay micelles, and then of course they get dispersed and move around in the soil profile. So yeah, the plagioclase, orthoclase become the clays that basically then help build that whole soil dynamic, right? So let's get into that because there's a good point. Okay, so what we had 420 million years ago, but we're going to have that same story now every day. And again, think of it, this is exactly what happened on your Great Plains after the last glaciation. So this is it. So basically, if you just have hard rock or solid rock or compacted soil or, stardust, 4.6 billion years, it had a supernova, created stardust, created the planet of these rocks. And these rocks are made of nutrients, whether it's phosphorus, calcium, zinc, magnesium. And there's mineral particles amongst all of that. So basically, that was in a sense what the Earth, what the rock was like 420 million years ago. You put a drop of water on that, and as Didi has showed us with a flower, it just runs off, right? No effect. And what life did, just as Didi showed us with the bread and the sponge and the whole petagenesis process, life basically, these lichens grew on this rock, solubilized them, and what they did is they created exactly the same mineral process. How many we've got? 1, 2, 3, 4, 5, 6, 7. Right, 7. We don't want to lose any particles, or we can actually draw, some of them are broken up to little clay micelles, right? No problems. Okay, so basically what is done, life has done is basically solubilized these, broken these up, and left organic detritus between those particles. And this detritus, just for figuratively, think of it as little carbon bed springs, right? Okay, and you straight away you get the kids out and they want to bounce on it, right? Sponge. Okay, so the whole business of creating a healthy soil, please.
You just said that those are just the plain rock morsels.
Yep.
And the water comes down. And then you said they leave this detritus.
Detritus. Okay. So
It must be regional.
no, it's okay.
But you said that there were, I forget what you said, but they're biological? You said
Yep.
life forms. Where did the life forms come from that is in those examples?
Oh, okay. Well, these are the lichens and
Where did they come from?
Well, they grew 420 million years ago from the ocean, from the life that evolved in the oceans, grew onto the land.
Life in the oceans.
Right, let's go back. Before my time, 3.8 billion years ago, there was a drop of lipid with a drop of liquid inside it, and you actually had a sort of membrane formed by an oil film. It's drawn a bit thick, actually. It's not quite that thick. It's a very, very thin oil film. And then basically this drop was able to basically do something quite unique. Okay, it was able to concentrate essential nutrients. So if there was 10 parts per million of phosphorus out there, it was able to concentrate 100 parts of phosphorus inside. Okay, phosphorus. But toxic elements that basically were, just say, cadmium, it was able to exclude that and just basically say if there were 200 cadmium outside, we had 2 cadmium inside. So really we had these semi-permeable membranes able to concentrate and exclude nutrients from that primordial soup. Okay? And in a sense, that created the first living cells 3.8 billion years ago. And that's the first life. And fungi are simply an extension of this. They're just this linear, tubular extension of exactly that process. Okay, so that's where we understand, to the best of our scientific understanding, life came from. And fungi are simply just an extension of that. And those fungi were then colonizing these rocks. And in breaking these rocks up, were able to create, in a sense, this matrix, because they were putting carbon detritus from their cell walls into that matrix. Okay? And in a sense, that then goes from a rock, which has a bulk density of 2.6 to 3.5 grams per cc, and that's a weight per unit volume, to a healthy soil which has a bulk density of about 1.2 grams per cc. So straight away you can see that healthy soil is made up 66% by nothing. Air. Voids of, just air, nothing. I mean, well, air is something, of course, so I should be precise. But the point is, it is made up of voids. And that's as simple as that. You see, nature has simply taken sunlight, CO2, water, created carbon, through these plant processes, microbial processes, just added those to this matrix, this mineral matrix, and has created a healthy soil, which is just made of mineral particles and these bed springs, or these carbon detritus. But what's powerful about a healthy soil, and really comes to the guts of our whole sponge discussion, now we have 66% of the volume, which is available for infiltrating and retaining water, just as Didi showed us in her bread example, right? Now this soil can infiltrate water, retain water, and sustain living plant growth for far, far longer, the longevity of plant growth. Because of these voids and because of the surfaces they've created, this healthy soil can vastly increase the availability of nutrients. Here we had essential nutrients for plant growth, but they were all locked up, unavailable, inaccessible. Now we have the phosphorus, the calcium, the zinc, in a sense all exposed for microbial activity. So the bioproductivity of that soil increases exponentially simply by creating these surface exposures, just by having the voids, by having nothing. Because we've got nothing in this soil, voids, the rootability of this soil vastly increases. So roots can grow and proliferate and penetrate. Instead of 6 inches, they can go down to 6 feet, 20 feet. So the volume of soil resource that is now available for plant growth and the drawdown of carbon that we talked about earlier is, again, exponentially increased. So the whole bioproductivity of these healthy soils, the resilience of those soils, the capacity to infiltrate, to buffer, to extend life, vastly increases. In a sense, this is what nature did to create the biosystem, to create the hydrology. And again, in a very simple form, that's all we have to do. All we have to do is just do what nature did. We use plants, we use microorganisms. Okay, so here we have our plant, we've got sun, CO2 and water, we've got photosynthesis, and we're putting stable soil carbon into the soil because the fungi and the organisms that convert the sugars from photosynthesis into stable soil carbon, which is just this organic detritus or bed springs. And that's exactly what nature did. She just took sunshine, CO2, water, through plants, made sugars, made stable soil carbon, unique material. It's the only known material in the universe that reverses entropy, but that's another physical debate. You know, the only thing that doesn't get rundown of energy. You see, normally we have solar energy coming in and it gets dispersed and dissipates, and this process of photosynthesis and its storage of stable soil carbon is in fact the only known process that actually goes the other way from dissipation. But putting that in bed springs into this healthy soil, you profoundly increase the productivity, resilience of that soil. Okay, so that's what nature did. That's how we created the biosystem. That's how we created the world's hydrology, the Earth's hydrology. And of course, that's how the Earth ran 95% of its heat dynamics and its natural hydrological cooling. And so for us, it's again very, very simple. If we've got to draw down 20 billion tons of carbon, if we've got to rebuild this sponge, it's easy. We say, hey, let's just copy nature. Simple. Okay, so how do we copy nature? We've got the model there. So we sort of go back to the textbook, go back to primary school, and it's all as simple as A, B, C. And again, here we go. Here's our plant, because we know it's all about plant growth. And it's all about ABC. You know, like it's that simple. All we have to do is what nature did. It's all about ABC. A is about agriculture, both in terms of field cultivation, but also now urban agriculture. We'll come back to that later because it's really powerful. It's a really important, empowering breakout that we want to talk about. And agriculture is, again, where we've been dominant because we live above the ground and we're all about maximizing yield, weight, okay, because that's what we are, alpha males, maximizing weight, yield. And we're still in that game, right? So A is okay. But what we don't recognize, because we live above the ground, we only see things above the ground, but we're only seeing 30% of the biomass which is in the tops of the plants. What we tend to not see is the 30% plus that is in the root systems. If you go to your bluegrass prairies, you've got root shoot ratios of 5:1, so already 80% of the biomass is down under, not up here, for a very good reason. But the point is we just see things above the ground and we sort of miss some of these very important things. We also miss, there's 60% there, there's up to 40%, 30 to 40% of the nutrients that are actually exudated out from the roots as sugars and amino acids and various sort of sugar substances, and these are critical for feeding this microbial ecology that drives the formation of the healthy soils. So these support a vast population of the fungi, the bacteria, the protozoas, the nematodes, the actinomycetes, the collembola, the earthworms, that whole life in the soil. There's 10 times the weight of living animals in a healthy soils down under than there is animals or humans grazing above it. And all of those organisms are driving the solubilization, fixation, access, uptake, cycling of nutrients, constantly just driving the energetics and nutrient availability and productivity of those systems. So 10 times the biomass. These fungal hyphae, 25,000 kilometers of fungal hyphae per cubic meter of healthy soils. Twice the diameter of the earth per cubic meter. We count them, but not with a ruler. But the point is a massive proliferation of fungal hyphae growing all through these healthy soil systems, again, solubilizing nutrients from surfaces, fixing nutrients, accessing, taking up, cycling nutrients. So massive activity and diversity in the life of our soils. And so as Didi mentioned, yes, you can put a spade in the soil. They'll eat the spade before you hurt them. But the point is that that soil is a living organism. It's a living microbiome. And really it's managing and enhancing that microbiome, as we'll show in a second, is critically important. Okay, so agriculture is important, but we've got to look at these other parts. We tend to forget them. But also it's not important, what's not important is how much yield we've got. What is the weight of yield we produce above ground? That's fair enough. But what is really important, what happens to every gram of carbon that was being fixed by photosynthesis? Okay? Not how much we produce, but what happens to it. And there's only two things that can happen to that carbon. And only two things that have happened to that carbon for the last 420 million years. Two things. It can either burn or oxidize. Of course, back to CO2, can't it? Or alternatively, it can turn into stable soil carbon. Okay, and here we are. We're back to this situation. It can either oxidize off or turn into bed springs. Pretty simple. Okay, and so our whole future management of biosystems is all about BC ratios. How much do we let burn and how much do we let get fixed into our stable soil carbon? We just talked a second ago about the tall blue stem prairie grasses, root shoot ratios of 5:1. Yeah, they're putting 80% of the carbon they fix into the soil, building healthy carbon, building sponges, building bed springs. And you go back to this story with the bluegrass. Okay, if you were on the Great Plains 9,000 years ago, you would have had glacial outwash till. Clays, rocks, gravels, swamps, but just mineral wasteland. And in the space of that 9,000 years, it's this process, these tall bluegrass, prairie grasses, pumping carbon into bed springs that has created some of the world's most productive soils, 10 meters of beautiful prairie soils, 8% carbon content, able to retain, infiltrate rain, retain that rain, extend longevity of growth, green growth, maintain massive populations of herbivores, resilient, productive biosystems, until we came along. But that's another story. Okay, so the capacity of these systems to grow, this capacity to grow healthy soils and fix carbon is prodigious. But then we come along. And what we come along is, we come along both trying to grow things better, but in trying to grow things better, and I don't want to be rude, we sort of have this moron agriculture, M-O-R-E-O-N, right? Moron agricultural strategy. Okay, and we add more, we can clear, okay, let's go through it. We can clear, we can burn, we can cultivate, we can over-fertilize, we can irrigate, we can fallow, and perhaps worst of all, we can add biocides.
I'm going to translate a couple terms there. Cultivate is tillage or rototilling, that kind of thing, and fallow means to leave the land bare, not grow anything. So
Okay.
bare fallow. Yeah.
Right. But they all do the same thing. They all oxidize carbon from the soils back into the air. Okay, all of these processes in excess, I mean, let's not be pure about it, but in excess, all of them are driving carbon, burning off bed springs, putting it back into CO2, collapsing soils back to compacted, impervious rock, flour, lower productivities. So the tragedy is, in a sense, what we've been doing in our agriculture is we've invested now 40% plus of the net value of our agricultural production into these inputs that are actually driving this CO2. And of course, a lot of the CO2 comes from our fossil fuel use, but for the last 6,000 years, well before we were using fossil fuels in any quantity, we've been oxidizing carbon from the landscape. Okay, we used to have 8 billion hectares of primary forest on this planet. We've cleared 6.3 billion hectares. We've cleared 6.3 billion hectares, and basically some of it's regenerated, as in the US, in the North New England areas, in your northeast, but we've now got 3.5. So we've gone from 8, cleared minus 6.3, and we've basically regenerated, so now we have 3.5 billion hectares of forest on this planet. We burn every year, Jim was into this debate, we burn every year 350 million hectares of forest. 10% of that residual we burn every year. Every year we burn some 2 billion hectares of grassland, crop stubbles, and rangelands, all driving CO2. As Didi said, we cultivate the land. When we cultivate the land, we expose it to ultraviolet radiation that kills the microorganisms, and of course it oxidizes carbon. We add excessive fertilizer. Every gram of excess nitrate, for example, we add to the soil, as in a compost process, oxidizes 30 grams of carbon. That's just the biological composting reactions. Okay, we irrigate, and basically, again, we're just accelerating, or we're restricting the fungal growth, we're sort of stopping, different organisms growing, restricting the bioproductivity. We fallow, obviously that's just starvation, concentration camp starvation. If the fungi haven't got exudates, they can't grow, and everything just slows down and dies, or just sits in a resting dormant stage until plants come back again. And of course, if we add biocides, it's just killing all these things outright. Okay, so we've done an enormous lot of damage. Conversely, in a sense, this is what regenerative agriculture is all about. We can focus on C, and the question is how much of these roots and these root exudates can we turn into humates? That's humus, you know, all the different fulvic and humic acids. So this whole category of humus, effectively the composting type process. So how do we maximize that? And the other important thing is these mycorrhizal fungi, these fungal networks, a 25,000 kilometers of fungal network. They're all made out of chitin. It's a glucosamine. When the fungus moves on, it leaves behind the cell wall. That chitin cell wall turns into compound glomalin. Yay! And glomalin and humates then form the glue that aggregates soil and actually creates bed springs, right? Just bring it back to bed springs. Go for it.
So how much of the CO2 in a healthy soil is put back by bacteria? That is, when I look at soils, the bacterial microbiome
Yeah.
in soils is the most complicated one on the
Oh yeah,
planet.
absolutely.
More than even in my
Yeah,
gut.
yeah.
So the question is, what about that? Can you
Okay.
alter the
Yeah, we alter all of that, but basically the bacteria don't bring it back. Plants bring it back because only photosynthesis can, you know, fix the carbon. But of the sugars and of the cellulose and lignin, it's the question: can we use those bacteria, those fungi, to bring it back? Right?
Right. So the
And
fungi is the long.
Yep.
thing.
Yeah, and the bacteria, the single
But
cells.
Bacteria also
Yeah.
add up.
Okay. And basically the fungi, well, the fungi do most of the work, but we're not sort of scoring because it's a zoo down there, and really we've got a healthy zoo, right? But we can do better than that. You see, this is then the stable soil carbon, but even the litter up here, or even the stubble or the litter, right? The plant material that we haven't harvested as grain, nature involves these other very, very clever things. They're called mobile biodigesters, because they're trying to, just what you're saying, they're trying to get this stubble, this plant material back into the soil, and they develop these mobile biodigesters, and they were big bags, they call them rumens, full of bacteria. Okay, but these things had to move around, so they didn't have wheels, forgot about wheels, they put legs on these things, and they've got a business end with ears and eyes, and a mouth, and they've got a business end out here which is putting biofertilizer down and stable soil carbon, and these things actually produce protein. Okay, so nature basically evolved these mobile biodigesters deliberately to do what you just said, to turn optimum bacteria conditions, to turn these cardboard litters, because if we didn't do that, all this litter goes up as fire. Okay, so we've got this beautiful thing. Do we either biodigest or do we burn? And if we burn, we go back to deserts. We go back to hard rock desert.
And that's what we're seeing in California, is that they've gotten rid of their mobile biodigesters, and there's all this fire
Yeah.
kindling building up on the
Yeah,
landscape.
so if you don't eat it, it's going to burn. And the first lesson of ecology, if you can't beat it, you eat it. That was Odom. Come on, you read the book, you know. Yeah, go for it.
And the hooves break up the surface soil.
Absolutely. And so there's a lot more ecological advantages because these herbivores, they're moving around, they're breaking up surface soil, they're spreading seed, they're spreading biofertilizer. So the wise integration of herbivores, particularly in grasslands, critically important. Grasslands evolved 50 million years ago, and they exist only in a symbiotic association with the herbivores. If not, those grasslands will burn and that whole biosystem crashes back to desert. Okay, so really it's a absolutely knife edge, ecological balance, grazing ecology, and of course we manage this. So the important thing is we manage all these things, and we can manage B and C beautifully through just smart, ecological, regenerative agricultural practices, which is of course what Adam and Paula and Didi and all the practitioners about regionally, locally, saying how do we make this thing sing and dance first? How do we make C dominate?
And where does methane production by the ruminants fit into this?
Right, okay, good. Let's look at methane.
Yeah,
Yes, good. No, methane, because these are very, very important questions. You, me, anyone with a gut produces methane, right? Because we've all got anaerobic bacteria. So these things produce anaerobic bacteria, no question. And of course, under anaerobic bacteria, we produce methane. But also, because these herbivores create green grass, because as I just said, they are the critical thing to keep that ecological health of those grasslands and stop them from burning. That green grass, and we'll come back to more of this later, but it's really clever, nature's clever, it produces, of course, transpiration. It produces, of course, water vapor, right? Water vapor. And when sunlight hits water vapor, it photooxidizes and produces hydroxyl ions and hydrogen ions that form bicarbonate ions, right? So you've got sunlight on water vapor photooxidizing the water vapor molecule into hydroxyl ions and bicarbonate ions. And basically these hydroxyl ions are, as you know, free radicals, enormously aggressively oxidative, and they will basically turn that methane rapidly into CO2 and water. Okay? So we've got this process. Now a healthy green pasture will produce about 100 times the hydroxyl radical photooxidation than the herbivores grazing it have the potential to produce. 100 times. There's also methanotrophs in the soil, but hey, that's just the icing on the cake, right? But the real guts is this hydroxyl thing. Now, methane has been 700 parts per billion through the last couple of 10 million years plus in the atmosphere. We've had massively increased and higher numbers of herbivores on this planet. You know, if you look at the buffalo, if you look at the wildebeest, if you look at the springboks, you know, all these natural grazing things, far higher things. And so basically, we've had far higher methane production previously, but methane levels in the atmosphere have stayed constant at 700 parts per billion, thereabouts. Recently, they went up to 1,700 parts per billion, and of course, that was due to Russian oil gas fields after Yeltsin and the USSR breakdown, not having any maintenance for 10 years, and the fugitive emissions were prolific. They've now gone up to 23, and it varies from place to place. And again, some nations have been fracking. And of course in fracking, we don't know which, but apparently there have been, some nations have been fracking, and again, the fugitive methane emissions from that fracking are prodigious. But there's a patsy in this game. They're called cows. Okay? And so really, it's a really neat thing because cows can take the blame. Hey, these cows produce methane. We just look at, yes, a cow does produce methane. We, you, me, produce methane. But cows are the patsies. They can be vilified, right? Because they produce methane. But the point is these cows are actually maintaining these healthy green pastures, maintaining that photooxidation potential, particularly at high latitudes. And the real issue of methane, and it's not in the literature, but it's really the real issue about methane is our methane hydrates that are sitting in high latitude, sedimentary, ocean sediments on continental shelves. They're bubbling up. The Russian Arctic is now like lemonade with methane coming up.
Tundra.
And the tundra is releasing methane. And the only thing, and methane previously to our knowledge has caused mass extinctions. You know, bigger methane burp is one of the most dangerous things we face in this extreme climate over there. And the only thing that's going to save humanity or much of life on Earth from a methane burp is cows. Because if those cows are there, or the caribou or whatever, producing enough sustainable green pastures to produce enough photooxidation, enough methane, enough hydroxyl radicals, yeah, we've got that balance. We've got 100 times the hydroxyl from green pastures compared to the methane from the cows. So, yeah, we're playing Russian roulette.
How do we die from when we get that bird?
How do we die?
Yeah, what kills us?
What's the mass extinction?
Oh, what kills us?
Breathing it.
Yeah, well, no, it's not so much breathing it. Yeah, I don't know. There's lots I don't know.
It's 100 times more potent than CO2 as a greenhouse gas.
Yeah, it's 100 times, absolutely. It's 100 times more potent as a greenhouse gas. I know, but the point is that, but the question is what parts per billion methane has to be in the air before we asphyxiate? I don't know.
Oh, no, I think you meant what causes the mass extinctions from methane.
Oh, yeah, well, look, okay. Look, I don't know, but geologically we've had time where there's big geological outpourings of methane, and quite frankly, that's been associated with, do you know the answer?
In that part, it's so much more warming that you're getting that feedback.
Okay, so it's a warming feedback, okay?
But the thing I want to point out here, and Walter's done a great job, is these bioreactors that walk around, we don't want to keep them in feedlots.
Oh, no.
Great. Very different thing.
Absolutely.
Be out making grasslands.
Absolutely. No, look, no question at all, because these animals are designed to eat cellulose and lignin, not starch, and of course they produce more methane on starch, but you don't want to eat the meat from them because the omega-3 lipids are just so high, don't touch them. No, look, absolutely with that. Yep.
So would it actually be feasible then to take ruminants out to the Arctic tundra?
That we don't have to.
In order to help to...
Okay.
Yeah.
Yeah, okay, we don't have to take ruminants there. They're there naturally. The Lapps manage vast herds of reindeer. Canada, Alaska manage vast herds of caribou. All I'm just saying, nature has got these mobile digesters already in position. We just have to start respecting them and understanding just how powerful that is. But you're absolutely right. That is the frontline defense for a methane burp, a tundra methane release. If we don't have them, if we let those tundras dry and burn, as we did in Canada, Alberta, northern Alberta, Fort McMurray, wasn't it? Yeah. 2 years ago. It's again cactus, not just for burning, but also from the methane story. You had a question, yeah?
Yes. So I understand you to be saying that the damage caused by the methane emissions of cows is outweighed by the benefits of breaking up the soil and the manure fertilization. Is that right?
No. Yes, the manure fertilizing is a plus, but no, we're saying here's a triple plus, many plus, because these grasslands, these healthy fertilized grasslands maintained by these herbivores, putting water vapor up there which photooxidizes, breaks up into hydroxyl ions, and those hydroxyl ions are the things that eat up methane for lunch, breakfast and dinner. So these things are producing 100 times the methane that the cattle are actually producing, right?
Oh, wait, no, the 100 times what's needed to break down the methane.
Yeah, it's 100 times the what's needed to break down the methane that the cattle are producing. So there's a very net positive release of these hydroxyl ions, and the excess 99 will be able to sort of help balance any burps from the tundra. So it's more than just fertilizing and carbon fixation. It's actually this active photooxidation. It's all okay. There's a detailed, peer-reviewed, proven literature, soil microbiology literature on all this. Atmospheric physics. It was all done in the 70s. I'm just trying to think the names of them, but basically, no, it's all documented. It's never come into the climate debate because we've always looked at. See, we define a context as here's a bad guy, a cow producing methane. Just as we've been here, we say here's a bad guy, CO2 coming up. So we blame the symptom rather than looking at the process behind the symptom or looking at the bigger systemic context in which that process works. Yeah.
But if you could make some kind of a calculation or assumption about how much
how big a methane burp there would be coming in our future, how many, what kind of increase in healthy prairies and grasslands loaded with buffalo again,
but I mean,
whatever, would it take to counteract?
Well, when will the meteorite hit the Earth, right? I mean, we don't know, and we have no idea when methane will come up, in what volumes, where. But the point is, all we can say is, where's the insurance policy? Where's the natural buffering? What's kept us basically stable? As the young lady said, can we avoid stuffing it up?
I'm going to suggest
Yeah,
because
let's
there's
time.
a really big piece that Walter hasn't even spoken about that kind of is going to address the cooling that we need to prevent the melting of the tundra, prevent the
Yeah.
We haven't even gotten there yet. Let's go there.
Yeah, let's go there. Yeah. Oh, okay. Well, look. Oh, okay. Okay. No, that's good. That's good. Well, if we got till 7, I can have a drink of water.
What happens to the 3 watts?
That's where we're going.
No. Okay, what happens to the 3 watts? Good question, but we're gonna do it because Didi's in charge, so I'm gonna have to wait till Didi allows me to answer that. But look, so what we've been talking about, in a sense, this whole different picture of what's the new climate solutions, how do we step outside of the tunnel, the black hole we've created for ourselves on the CO2, and sort of open new windows and open new opportunities laterally by embracing this hydrological dimension. But the key point is, we've gone through why, we've gone through what, we've gone through how, the ABC, and it's all about rebuilding the Earth's soil carbon sponge. See, we didn't go through all that, did we? Can I just backtrack a little bit? Because I just wanted to make a point. See, we got sidetracked. I've got ABC here. So we say, look, the whole critical thing is the balance between B and C. But of course, we've left a field here vacant. And in nature, there's never a vacuum, there's never a vacant thing. So we've got to have another thing, D, which are the dividends. And this is very important because this is really the guts of agriculture and where we're going. And if we put carbon into the soil in C, for every gram of carbon that we put into that soil, as we've seen here already, for every gram of carbon, we can hold 8 grams of extra water. Okay, and you can see that from the sponge, the bed springs, the voids. Hey, we can massively increase the water retention, infiltration, and then longevity of green growth. And that's the important thing to understand. Like all of our Green Revolution stuff where I started research, I didn't tell you what I've been doing, but when I started as a researcher, was all about how do we increase the yield of plants, Green Revolution, right? And we do genetics and fertilizer, and if we can get a 30% yield response, we get a new white lab coat, a clipboard, and line up for a Nobel Prize, right? It's big stuff. But basically, at best, we can do 30%, 40%. But if we increase the longevity of green growth, there's a rain, we've got a sponge, instead of the soil drying and we've got 10 days worth of growth, we've got 100 days of growth now because of the sponge. We've increased the longevity of green growth 1,000%. Just through building the sponge. So the multiplier effect of longevity of green growth and extending drawdown, extending productivity, extending resilience is powerful. So 1 gram of carbon, 1 gram of carbon, 8 grams of water. Every gram of carbon we put in the soil massively increases the biofertility of that soil, as we've explained, as the nutrients become available. 80% of the fertility of soils isn't about how many nutrients in that soil in total, how many nutrients in total. It's about the availability of those nutrients. It's about the microbial solubilization, fixing, access, uptake, cycling of those nutrients. So the whole business about fertility is about the microbial ecology of the soils, not the content or how many morons we put on. Well, yeah, but no, we're not going to answer that because it's, yeah, it's all part of the game. Okay, the other thing, every gram of carbon we put into the soil, as we've said here, massively increases the rootability, the volume of soil we've got access to. Powerful exponential increases. And the same goes with then the microbial activities, disease resistance, resilience, productivity. The point we're making with D is simply by increasing bed springs, we can drive productivities, as nature has, massively. You know, we've got rainforests on sand dunes in Queensland where I was working when I was working in CSIRO. The world's most bioproductive terrestrial ecosystem, effectively on crushed glass with next to no nutrients in it, but every molecule is moving 1,000 times faster and therefore giving that productivity because of this microbial activity, right? So it's not how many, it's Mae West, isn't it? It's not the number of men in my life, but the life in my men. Well, you're Americans, come on. I'm just quoting you. You know, another one, President Roosevelt, a nation that destroys its soils destroys itself. That'll balance, you know, that makes it back on an even keel, doesn't it? Get away from Mae West. The point being, though, that, see, this is in a sense how nature drives productivity. You know, not by Mack trucks putting fertilizers on, not by inventing biocides and all that sort of, not by cultivating, simply by increasing soil carbon. More powerfully, because of these dividends, we negate the need for all this moron stuff significantly. Okay? Because why do we need it when we've got carbon bed springs? And so our innovative farmers are doing 100% of the yield, but they're getting 300% of the quality, the nutritional integrity in their food grains. They're doing it with less than 20% of the inputs, less than 10% of the risk, 300% the reliability, and 500% the natural capital, asset, land, soil regeneration value. You see, these are dividends. Okay, so the whole basis of regenerative farming, the whole revolution in agriculture, taking agriculture from the 19th into the 21st century, is all about rebuilding healthy soils, rebuilding that sponge. Because without that sponge, we've got cactus. Nothing. Dead. Desert. Now we can forget all about that and we go into the important stuff. Because once we have a sponge with water in it, obviously, what we have, in a sense, the capacity to grow biosystems. We already talked about that, longevity of green. And we've got transpiration, right? Water going up is transpiration. And you and I and everybody knows for every gram of water that transpires, it has to go from liquid to a gas. And to go from liquid to a gas, every gram needs to have 590 calories of energy in its latent heat of vaporization. Simple physics. And so 590 calories of energy have to be taken from the soil surface, from where the water is, and from the vegetation. And so we can't avoid but cool this surface. That heat, of course, goes up when this water condenses. It again gets released, and most of it goes back out to space. Okay? Nature has really driven the hydrological cooling of the planet by these latent heat fluxes. Even now, with half of the green vegetation on this planet, the residual green vegetation we talked about, 24% of the incident solar radiation, you know, that 342 watts coming in, some 85 watts per square meter, is constantly taken back up through these latent heat fluxes. Okay, so that green vegetation is constantly taking 24% of the incoming energy that's striking the surface and taking it back out to space. So if we 5% increase in green transpiration, we can effectively negate 3 watts per square meter, roughly, right? It's obviously many factors of things. So the fact is, yeah, the 3 watts per square meter, how do we cool the planet 3 watts per square meter? Simple, increase transpiration 5%. And we're running at half of what there was 8,000 years ago. We're running at 50% of what there was. Okay?
I was just thinking, think about all the bare ground that's out there. It's not doing any transpiration.
Yep.
Bare ground is what's killing you.
We'll come to that. Okay, come to that. Come to that. Okay, so here we have, in a sense,
Just a brief comment. There was, in the upper Midwest, they stopped leaving land fallow, and a study of that showed that just that one thing, covering that land all year round with green things, brought down the watts per square meter by a factor of 6 watts per square meter. That's double.
Yep. I live in a city called Canberra, which is Australia's natural capital. It was designed and built from 1913 onwards. Marion Mahoney, Walter Burley Griffin won the prize. They made a landscape city. It was a leading city for the 20th century, you know, what urban future habitats need to look like. And of course what they did, it was, I mean, Canberra initially was what we called a clapped out, arid, dusty, dried out sheep paddock. And basically they built an urban forest and really created a whole new mesic forested urban forest environment. It's now 7 degrees centigrade cooler on a hot summer's day, you know, 35, 40 degrees centigrade, than the adjacent urban heat island concrete new suburbs, 2 kilometres away, right? 7 degrees centigrade cooler. So absolutely, and it's all just because of latent heat fluxes. So again, we in Canberra, we've got a thing, you know, from the grassroots called Cool Canberra, and it's all about urban trees, about porous pavements, about sponge infiltration to keep these latent heat fluxes. But it gets better, so let's keep going. Obviously, we've got these hazes and these latent heat fluxes condensing into cloud, or little droplets, and of course releasing the heat. So we end up with massive numbers of cloud micro droplets, right? Okay, but these are far too small to fall out as rain, and of course they sit up there as hazes and as clouds. But then they'll basically form these nice white fluffy things, right? Somebody asked about clouds before, right? So they'll form dense, high albedo clouds. There's a coalescence process involved, but we can go through the physics, but I don't want to waste time on it. But the point, these dense, high albedo clouds, they basically reflect, because it's an albedo effect, they reflect that incident solar radiation directly back out to space. It doesn't even get to the soil surface. You know, when a cloud comes over, hey, you're reaching for another jumper. It's significantly cooler. These guys, globally, 50% of the Earth's surface is covered in, dense clouds at any one time. Well, certainly used to be, it's getting less, but 50% of the surface of the planet is still covered in clouds at any time. These guys on average reflect 120 watts per square meter back to space. Okay? About a third, roughly, of the incident solar radiation is just reflected back out to space. So again, the same analogy, a 2% increase in cloud will offset 3 watts per square meter. Okay, and cloud can only happen can only happen if we get micro droplets, and they can only happen if we have a sponge that's transpiring water up into the air. Okay, so you can see all the time we bring it back to the sponge, because the sponge is a fundamental driver, but also the sponge is what we influence. That's our point of agency. A, B, C, D, it's what we can do. Every square meter, every acre, every region, every nation. Grassroots empowerment of action. Okay, so there's clouds. But we talked about the sponge being critical, but that's not good enough having clouds, because we also need this next guy. We need raindrops, don't we? Because if we have a dry sponge, cactus, no good. So we need rain. And it takes about 1 million of these cloud condensation droplets to form a raindrop, because it's got to coalesce about 1 million of these cloud microdroplets to make a raindrop that's big enough, heavy enough to fall out under gravity. There's 3 things that actually allow you to do that. They're called precipitation nuclei. Okay, rain can't occur just by itself. They have to be precipitated through these precipitation nuclei. 3 things. There's ice crystals, and of course they're very important. High altitudes, high latitudes, and frontal rain. It gets colder, it forms ice. You know, a glass of whiskey, ice will coalesce on the outside, condense on the outside. Same process. So there's ice crystals. Over the ocean, of course, we have a lot of salt. Spray comes up from the oceans, and again, salt, sea salt. We know on the fish in the ocean, shake the salt shaker, it's all gluggy because it's hygroscopic. It sucks up water, won't come out, and again, it's basically coalescing these droplets. And of course, it's these salts that we use for cloud seeding, where we use, for example, silver iodide to create artificial rain. Basically, we go up with aeroplanes, atomize silver iodide, drop it into particular types of clouds, and consistently get 20-30% more rainfall through that process. Okay, but by far the most important thing, particularly on inland areas and tropical and warmer areas, are not these, but this bacteria. There's certain bacteria, and Louis Pasteur wrote about them, defined them, isolated them in the 1870s. He called them Aerobacter orogenes, because he certainly found them in all the air, but he didn't know what they were doing there, so in Greek that translated to, yeah, I don't know what they're doing there, orogenes, right? Well, he was a scientist, he's got to be objective about it.
So long as it wasn't erogenous.
Sorry?
Just so long as it wasn't erogenous.
Erogenous, yeah, well that's Parisian, isn't it? But the point is, there's bacteria, right? And so these in cloud, CSIRO, atmospheric physics again, detailed work we did, by far the most effective at nucleating clouds into raindrops, by far, orders of magnitude. But of course, atomizing bacteria to disperse in the atmosphere is a bit sophisticated, and until recently we weren't able to do that. But these actually are produced in nature, and of course what nature does, in certain forests, and again we've got this from the Amazon, a whole lot of studies, basically it's not just transpiring water vapor, it's also putting up bacteria. Okay, and so half the rain, this is from radioisotope studies, half the rain in the atmosphere, the Amazon, is actually driven by these bacteria. It goes up, transpires every day. 4:30 in the afternoon, you set your watch on it, it comes back down in a thunderstorm. And every day you've got this hydrological cycle taking heat from the surface, dissipating it upstairs, returning rain back to the sponge. Okay, and vast areas of forest have been cleared. We've talked about the 8 billion hectares of primary forest that we've cleared, 6.3 billion hectares of. So what have we done to our rain? We can write a song about it. Okay? And so this is a question again, by regenerating landscapes, can we actually start restoring these hydrological dynamics? Because these are critical if we're going to refill this sponge. Okay, so it all comes back to, cooling, cooling, rain, more cooling, cooling, cooling. Okay, powerfully natural, simple, safe processes to cool regions and the planet.
What scale does this small water cycle operate on?
Now this is, the small water cycle is when you have basically, here's a canopy and you've got transpiration and condensation, so it operates within this cycle. Now this is planetary, this is global. These are, the whole dynamics of clouds and rain at a global level, right?
I think in the Amazon, they've tracked at least three to five different cycles.
Yeah, there's 5 times more rain in the Amazon, if you measure how much is in those tin cans every morning, compared to what flows out of the river. Because every day that cycles round and round and round through these processes.
But each one extends the range of the Amazon.
Oh yeah, let's talk about that in a second, right? No, it's good. We can write.
Ice and salt and bacteria as nuclei. What about dust?
Okay, look, good point. Dust actually doesn't do, it's not precipitation. Dust creates haze nuclei up here, very small particles. So dust, aerosols, dimethyl sulfide, James Lovelock's stuff, they're creating actually haze droplets. We haven't gone into, there's a whole atmospheric physics of these hazes, but yeah, they're sitting up there. We've now got a pollutant brown haze from Cairo to Beijing, and basically just sitting there, heating the landscape, aridifying the landscape, killing the people because of the pollution effects. And again, they have to be, actually in that context, they're very, very damaging and negative, and they have to be condensed and coalesced into clouds and then raindrop to get them out. But that process isn't happening. But certainly dust, the Sahara, Saudi Arabia is driving that whole blanket of haze. And of course, no, look, let's not go there because there's a whole other chapter in atmospheric physics, because these hazes absorb both incident solar radiation in the liquid phase, causing global dimming, but we'll come back in a second. They're also the key thing that keep the water vapor in the atmosphere that drives the water vapor greenhouse effect. But we'll come into that in a second, right?
Just this week there was some news about the kind of estimate of huge numbers of viruses that
Yep.
fly around in the air, apparently.
Totally.
About that.
Oh, no, look, it's a zoo up there. And that's what Pasteur did. You see, Pasteur made a broth, and he said this broth has got contaminated by some living thing, these bacteria, these microorganisms. And so what he did, a very clever little experiment, he just took the tube of the broth, that was in a flask. He heated the flask, he bent the tube down so the tube wasn't open to the air. And of course, when it was bent down, bacteria couldn't fall into it. And you can still go to the Pasteur Museum in Paris, and there's still his broth. Don't eat it, it's probably lousy cooked. But the point is that it's still there as an uncontaminated broth. And so then he said there must be organisms in the air that are causing this. And so then the whole aerobiology sort of became a big deal. And he then went up to the top of Mount Blanc and opened a flask full of Aerobacter. And then basically Challenger went up in balloons, it went up to about 30,000 feet. Nearly froze to, obviously freezing oxygen and stuff. And again, collected air, and there's even Aerobacter up there. So yeah, the air is just chock-a-block of spiders, of pollen spores, viruses, bacteria. It's a zoo.
Of course, that grows mold on bread.
Yeah, it's Rhizopus, go.
So I want to get back to the Hadley cells, because as they change, aridity now comes in. So the question is, how does this change the Hadley cells?
Okay, we'll go to that because that's very important. I'm just trying to get another board, but I can't. I think I'll just have to wipe some of this up. Now hang on, we've already wiped all these moron inputs anyway, so we can have that space. Right. Okay, so the point of that whole exercise is that yes, we need rain, we can cool the planet, but it all depends on the sponge. And of course, somebody made the point previously, there's a vast difference where we have two land systems. Here we've got a land system with plants, grass, green, and here we have a bare land surface, right? Vast differences, because this one is both getting latent heat fluxes, so it's cooling, and very rarely does this soil here get above 20 degrees centigrade. Okay, because it's got latent heat fluxes cooling, but it's also got the albedo and shading and cover effect. But we know that a bare surface, whether it's soil, asphalt, roads or whatever, readily gets up to 60 degrees centigrade, right? Certainly in Australia. You know, you melt your feet. I mean, way past your feet, your shoes as well. Okay, and what it is, it's of course this incident energy coming in, heating these systems, and of course how much is actually taken back up. Vast differences in things. But there's again a simple fundamental law of physics, the Stefan-Boltzmann equation, because the Earth is a black body radiator. It's like a stove. And the black body radiator, the Stefan-Boltzmann says the re-radiation from a black body is proportional to a constant times the fourth power of the temperature in degrees Kelvin. That means temperature times temperature times temperature times temperature. So when we have two different surfaces, one at 20 degrees centigrade and one at 60 degrees centigrade, we get a massive, massive increase in the re-radiation of heat, infrared energy, from this bare, hot surface. Okay? Massive increase. Now, the punchline is, we all know that, but what we don't recognize is there's three things that control both the natural and the artificial greenhouse effect. The first factor is how much re-radiation there is. The second factor is how much of that is absorbed by water vapor molecules. And the third factor is how much is absorbed by CO2 molecules. Three variables in both the natural and the artificial greenhouse effect. And the point is, we have completely ignored in all our climate models the effect of land management and these bare soils and this re-radiation in driving the greenhouse effect. Completely ignored it because we said, oh, well, look, you know, that's just the planet and we're concerned about CO2. There's up to 40,000 parts per million water vapor in the air in these humid hazes. We know there's 400 parts per million of CO2, 406, let's be straight, parts per million of CO2 in the air. We know that each water vapor molecule, because of its molecular structure, holds 8 times, or can absorb 8 times more water than a CO2 molecule, 590 calories compared to about 72 calories. And yet, we're only concerned about this variable, and we can't do anything about that variable for 1,000 years. And we're saying, hey, doomsday, game over, can't go forward. And we're more or less saying there's a new solution to climate change because basically we control this guy, and this runs 90% plus of the greenhouse effect. We control this guy, we've just gone through that in terms of rainfall, you know, induction, etc., etc. And yet we're all focused on that. But we need this because this is the building blocks for building bed springs. So we're into building bed springs through drawing down carbon to build the sponge. But what we're saying is, let's just get real. You know, we've got a climate climate crisis. We've got 10 years, so let's start talking to the elephants. Because we can do this, and whether we do this instead of that is existential.
absorbs 8 times
Each?
as much heat as the,
Each molecule of water, this is 104.5 degrees angle. So each water molecule can absolutely be, because of its molecular structure, can absorb enormous quantities of heat, quite uniquely, right? And it changes the angle of that thing as it gets hotter. The CO2 molecule is basically a double bonded molecule. Because of the double bond, it's really quite rigid and locked in, right? Okay? And so its capacity to absorb heat through this bonding structure is about 1/7 and 1/8 of the water molecule.
okay, interesting.
But obviously it's a matter of how many molecules. I mean, there's a whole lot of variables at play. But basically we're saying 40,000 parts per million against 400 parts per million. Okay? So that's 100-fold different. And basically we've got this different absorption. 800-fold. But the point is, this is the elephant, the big elephant, mummy elephant. These are baby elephants by comparison, right? Okay, so really we've got, again, we're just talking about empowerment. So through our land management, we have an enormous, enormous capacity to both cool the planet but avoid these dangerous extremes that we're facing. There's another thing. When we actually re-radiate a lot of heat from these bare, dry, hard surfaces, obviously this heat is just energy, and so this creates a very high pressure dome, heat dome, right? Okay? And we talked about, I mean, this is the question I think you raised. So we create this massive high pressure heat dome because of this re-radiated energy. And so if we look at a country, and let's look at your country, because we've got the ocean, we've got the coast strip, we've got the coast range, we've got the Central Valley, we've got the Sierra Nevada, we've got Death Valley, and then we go on to the Western Plains. Okay, and the point is, if we, for example, take the Central Valley, and we clear that Central Valley in California, the San Joaquin Valley, of vegetation, what we do is we create a high pressure heat dome over that landscape, right? And of course we've got cooler, moist, low pressure air from the oceans flowing in, but it's got Buckley's, which is an Australian word for no chance whatsoever, to be able to push this high pressure heat dome out of the way.
What?
Yeah.
Sorry, maybe say all that again.
Oh, okay. So what it is, if we have cleared this landscape, we're in this position here, we've created a high pressure heat dome because of all the re-radiation coming off thing. We have, in a sense, this mountain of hot air sitting on that landscape. We have now low pressure air, which has got moisture in it from the oceans. There is no way in physics that this flowing into that area can actually, this moist air can flow into that area. Okay? And so really we are actually desertifying regions and climates through our land management, because we fundamentally govern where it is hot, dry, re-radiating, creating high pressure heat domes. Can I just make, I'm going to come back. Okay, and so if you look at the Sahara, or let's look at closer to home, here's this country. I should be able to draw this a bit better. And we used to have an Australian monsoon. The Indian Ocean is the world's biggest evaporation basin, and so basically we've got a lot of low pressure, humid air. Humid. But because we've now created this desert over Central Australia, very rarely do we get this humid air coming into Central Australia, so we remain and reinforce a desert. 6,000 years ago, Lake Eyre was a freshwater lake 25 metres deep. Central Australia was a savanna, grassland with gallery rainforests along the creeks. Of course, by burning and land degradation, and nobody's blaming anyone, the point is we create this high pressure heat dome and we prevent this humid air flowing in. Same as here. Same here, okay? So we have a profound effect By contrast, in the Amazon, because it's got low pressure forest vegetation, we've already talked about it's continually sucking more low pressure moist air into it, driving that rainfall. Except over the last 30 years, again on eastern Brazil, Belize, we've actually done a lot of degradation, we've done a lot of burning, and for the first time we're breaking down this heat flow. For the first time also we've had a hurricane form in the South Atlantic, never been recorded before in history, because instead of that low pressure air, moist air being able to go and getting sucked into the land, it's building up, building up, building up till it becomes, in a sense, hurricane intensity. The young lady?
So does this mean that if you want to reduce the strength of hurricanes and rejuvenate the land more toward the center of a land body, that the areas near the coast are very important to kind of work on first if you had to choose? Which land areas you wanted to really rejuvenate?
Yeah. Look, we don't play, I mean, we can't play God, which area is best. But no, you do all of it as much as you can, right? But I agree, if you have a arid area there, you're going to have a buffered or preventative zone, right? So yes, you want to do it. These are pretty big continental powerful forces. There's an old Chinese proverb, it comes back to answer your question. They said, when's the best time to plant a tree? And the answer is 20 years ago. And then the second, when's the second best time to plant a tree? Now. You see, and there's wisdom there, because so we just got to do every square meter, every area, every courtyard, every balcony, every nature strip, every guerrilla gardening, every farmer. Okay, and so that's really what we're facing. But you're definitely right. In this coastal range, okay, what's happened, we've been burning these coastal forests. There used to be beautiful oak shelter woods on that range. They've been largely degraded for a long time in the Spanish, and then overgrazing and overfiring. And yeah, the question is, have they prevented humid air flowing into the Central Valley? Certainly we know that the Sequoia sempervirens, which is a coastal forest, they get 70% of their moisture from fog, dew, harvesting from these onshore humid air flows. But then it stops. And the question is, previously, Lewis and Clark, 1812, 1815, how much did that humid air extend? Because we know the Central Valley was this absolutely Garden of Eden paradise of wetlands and green pastures and rivers. It's just beautiful, ducks, geese, you name it, right? Yep.
So that stopped the orographic.
Orographic effect is, when you've got a mountain range and the air has to rise and obviously then cool as it rises, and often you get ice crystals. So that the rainfall, the snow on the Sierra Nevada, you'd say, is an orographic effect. And there's some orographic influence, but really these heat domes create their own mountains in effect, right? Stops it, right.
So what about desalinization?
Desalinization, yep.
I mean, getting fresh water from the ocean.
Yep.
And then pumping it into the land.
Yeah, okay, well, but desalinization takes a massive amount of energy to obviously, turn that salt water, because you've got to put it through a reverse osmosis membrane. So the question you've got to ask, what's the life cycle cost, because what's the cost of that energy in terms of carbon, pollution, etc.?
So the question that I'm still asking you is that the major aerodization is based on the change in the Hadley cell.
Yeah.
That's part of the global
Yep.
dynamics.
Yep.
And therefore, what are you going to do in that region where you're not getting rain?
Okay. Not for me to do, I'm just talking to you, but what we could do. Okay, as I said, there are humid hazes, air flows, all the deserts of the world have rivers of water flowing across them constantly in the air. 4% moisture content. Nature used to harvest a lot of that water through these processes. So I don't think it's a question of desalinization because of volumes of water compared to these natural forces. it's inconsequential. But the point is that, yeah, what is it that we've done to the land system that has prevented that condensation of these 4% moisture contents in those humid airflows? So like in the Middle East, yes, can we rehydrate deserts? Can we rehydrate? I mean, certainly that's what we're talking about in Australia. Can we rehydrate arid areas by creating vegetation that creates, the conditions for this condensation?
In the Middle East right now, you're going to get wars.
Yes?
Because of the
Water.
rivers, the Jordan River is dry.
Yeah, totally.
And the Turks are damming.
Yep.
So therefore, the only thing that has worked to save that, I mean, the question really is,
Yep.
you are talking about atmosphere, and the real question is, what about
Yep.
rivers
Yep.
and
Yep. Well, look, desalination is used to keep people alive. The 2 litres of water each of us needs minimal, but we use about 150 litres each because of showers and stuff. But basically, yeah, that's what it's used for. But there's no way at all that we can actually desalinate enough water to grow the food, and certainly not these ecological, hydrological processes. But 71% of the planet is ocean. Another 3% of the planet's surface is covered with lakes and what have you. And so there's plenty of water. This is the blue planet. It's just a matter of what have we stuffed up and what is it that we can restore.
And I think
Walter, so I'm wondering if we can
Yeah.
hold off the questions for a few minutes so you can kind of
Wrap up. Yeah. So look, let's do that. And really, I mean, basically, it's been good, this discussion, and so really quite finished with this whole thing. But the bottom line is, as we've gone through this whole extended discussion, yes, there are new paradigms. There are new doorways, new opportunities that we can use to naturally cool the planet, to address climate change, but also to secure the water, the food, the biosystems, the social stability that we just agreed depend on that. As the gentleman said, there's 7 missed meals between social stability and chaos. And that all depends on water, food, social stability, a la Syria. And the answer to this is critical, important. Yes, Mark Twain said, whiskey is for drinking, water is for fighting over. Okay, and it's true. And that's where it's going to happen. But the point is that these natural processes give us the option, an opportunity to secure endless, safe water. There's plenty of water on this planet, but it just has to be, we just have to come to respect it and rebuild the cycles. But the point of agency and the point of this whole discussion is it's about regenerating the Earth's soil carbon sponge. Because by drawing down that carbon to put the bed springs into those, between those soil particles, we can do it profitably, practically. We can actually rebuild the sponge, and as we've seen, ABC, etc., we can actually then restore healthy biosystems and a healthy future for California, but for all of us. Thank you very much.